Cardiomyocyte Action Potentials by Kenneth Holmes. The action potential of cardiomyocyte starts in phase 4, also known as the resting potential. Due to the levels of potassium within the cell, the resting potential sits at about -90 millivolts. During this time, voltage-gated sodium, calcium, and potassium channels are closed. Though there are rectifying potassium channels that remain active to maintain the resting potential. This resting potential is maintained until the cardiomyocyte is stimulated. The stimulus that drives our heart to beat comes from inside the heart itself. There is a cluster of cells located in the upper portions of the right atrium of the heart, known as the sinoatrial or SA node. This is made up of specialized pacemaker cells that utilize C-amp to send signals for the cardiomyocyte in the area to contract. This signal passes through the atrioventricular or AV node, which causes a delay to control the squeezing of specific chambers of the heart. Once the area has been stimulated, sodium will begin to enter the gap junction of neighboring cells. This will cause the membrane potential to rise or depolarize. As sodium enters the cell, the membrane potential will go from -90 millivolts to roughly -70 millivolts. At this point, the threshold is met. For cardiomyocyte, the threshold for the cell is around -70 millivolts. When the membrane potential reaches this point, the voltage-gated sodium channels will open, and there will be an influx of sodium into the cell. The massive change to the levels of sodium within the cell causes the membrane potential to rapidly depolarize. The depolarization of the cell, both in achieving threshold and after threshold has been achieved, are considered phase 0. During this time, the cell experiences rapid depolarization from the sodium entering the cell. The voltage-gated sodium channels will close during this process, and the intake of sodium will quickly stop. This will occur around +10 millivolts. After the voltage-gated sodium channels close, the voltage-gated sodium channels will open. This will begin the first repolarization phase, which is also known as phase 1. Voltage-gated sodium channels will remain open, dropping the membrane potential down to +5 millivolts. This will take us to phase 2. Phase 2 happens as the cell reaches +5 millivolts. This will cause voltage-gated calcium channels to open, allowing calcium to flow into the cell. This, along with potassium moving out of the cell, causes the action potential to be prolonged. The membrane will neither depolarize or repolarize. Instead, it will maintain at about +5 millivolts. This will maintain until the calcium channels close, allowing potassium to continue to be pushed out of the cell. Once the voltage-gated calcium channels close, this allows the removal of potassium from the cell to repolarize the cell. This is phase 3, the second repolarizing phase. As the cell is repolarizing, voltage-gated potassium channels will close, but the delayed rectifier potassium channels will allow for the transition of potassium back into the cell to achieve the negative 90 millivolts resting potential. Looking at this image, we can see the membrane potential starts out at about negative 90 millivolts. This is the resting potential, otherwise known as phase 4. From there, sodium starts to enter the cell through gap junctions. That begins the depolarization process. At around negative 70 millivolts, the threshold is achieved and voltage-gated sodium channels open. This is phase 0, the rapid depolarization of the cell. As the cell depolarizes, the voltage-gated sodium channels will close, causing the action potential to reach its peak at around positive 10 millivolts. From there, phase 1 begins, with voltage-gated potassium channels removing potassium from the cell. This causes the cell to repolarize until it reaches about positive 5 millivolts. This will cause the voltage-gated calcium channels to open and allow calcium to enter the cell. Calcium entering the cell counteracts the repolarizing of the cell, causing the action potential to be prolonged, which is why this is phase 2, the prolonging phase. The voltage-gated calcium channels will close, which will allow potassium to continue to repolarize the cell. The voltage-gated potassium channels will close, but the rectifying potassium channels will allow potassium in, as calcium and sodium are removed from the cell. This allows the cell to reach phase 4, resting potential.